So in this example, and we're going to try and stay as close to the numbers he had as possible, but I'm having to take a few liberties with what he did. So he jumps on after getting it spun up, and he starts by being right about at the edge. So let's just say that he is a point mass that's close to the edge, and I mean, I'm making this number up, but I don't think it's a big stretch. That it looked like we had a radius of about 2 meters. You guys saw it out there. You saw how big it was. Is that not an unreasonable amount? 2 meters. So that'd be these desks are about just a little over 3 meters across. So 4 meters would be here. That looks like about the size of the circle that we were seeing spinning. So that's kind of the number I'm going with. I did measure one that was at a park near my house, but it's gone too, and that was years ago, and it was just a little under 2 meters, but we'll work with the number 2, I think. He was spinning it in such a way that was making in the first instance, one rotation every 3 seconds. So that's 6.28 radians every 3 seconds. So that's about 2 radians per second. So I thought that'd be a nice number for us to use here for the initial speed. And I am 100% making this number up, but I don't think it's unreasonable. 100 kilogram disc. Having worked with with children's equipment before, it might be a little heavier than that, but that's like 250 pounds, and that seems about reasonable for what we saw there with the bars and everything. And since that was a full-grown adult, we'll say 70 kilograms for their mass. That's about 150 pounds. They might be more. They might be closer to 80, but they look like they're pretty small. So here's what I'd like you to figure out. Let's just take a quick minute. We need to find the moment of inertia of this system first. And this is a combined object, right? We have a single person on there, and we have the disk itself, so you're going to have two things in your moment of inertia. Second period had trouble doing this. Are you going to have trouble doing this? Do you need me to walk you through it, or is it something you think you can work on your own? Why don't you take a moment. There's two things, and you just have to add them together. So we'll say the person and the disk. So go ahead. Why don't you work that out, and then we'll talk about what I want you to do afterwards. How many of you agree with that? So I did 1/2 mr squared for the disk. It gives me 200, and then I just did mr squared because I'm treating the person as a point mass. So that's 70 times 2 squared, or 280. So that gives us a total moment of inertia of 480 kilogram meter squared. Now, the angular momentum of the system is going to be the product of the moment of inertia and the angular speed. So we have a total moment of inertia 480 and an angular speed of 2. So 960, and the units here are kilograms meter squared per second. Now this part I want you to do on your own. The person in the video moves from the very edge to the very center. When they're in the center, their mass basically stops contributing to the moment of inertia because they're standing at the very center and they are not particularly wide compared to the size of the merry-go-round. If you want to use them as a disk, then assume that they are a disk that's maybe 20 centimeters in radius. Does that make sense? So you could simplify it and make them a disk, but if you do, 20 centimeters in radius. Now, the system didn't experience any external torque, so this will have to equal the angular momentum after he moves to the inside of the spinning platform. So what I'd like you to do is figure out how fast is the platform spinning after they move from the outer edge to the inner edge. But like I said, if you're one of those purists, and you want to say, well, he's standing there, he must be doing something, he must have some inertia. True, but that's not how moment of inertia works. But let's just say, okay, he's a purist, he's a disk. 1/2 70 times 0.2 squared. That will be his contribution to the moment of inertia because his mass is very much concentrated at the center. It's not spread out through the entire disk. So that's going to be small. 70 times 0.02, right? Which will be 7 times 0.2. Is that just 1.4? So 1.4 plus 200. Can we just make it 200 since it's just 201.4 instead? You guys good with that? I said they walk to the center. They really don't contribute much to the moment of inertia. So that changes the moment of inertia dramatically now to 200. And then suddenly we get this pretty big increase in angular speed. 960 divided by 200. 4.8. Now, I mean, you watch the video, that's what happened, right? They were traveling, pretty slow, and then they moved to the center and start traveling really fast. Now, this part is not a huge deal, and I don't think this is a surprise. You watched it on the video, you saw it happen. So here's what I really would like you to do. What happened to the energy of this system? Right? This system had kinetic energy. There's kinetic energy before the gentleman walked to the center, and there's kinetic energy afterwards. Please calculate both kinetic energies. So calculate how much kinetic energy the system had when he first jumped on there, and then calculate the kinetic energy after he walked to the center. I'm not asking very much here. So, and I'm looking at the people I know who probably are having difficulty. Come on, folks. There's not much here. And, well, the guy at the center is now standing at the very center. And I said we could model him as a disk, right? So I put a new kind of calculation for his moment of inertia. He still has 70 kilograms of mass, but because he's standing at the center, if he's a point mass, his R is 0. But let's say he's no longer a point mass because the axis of rotation is through him. Well, he's only like this wide. That's like 20 centimeters. So if we estimate him as a disk, his contribution to the overall moment of inertia only ends up being like 1.4 kilogram meter squared. That's why I just left it at 200. I mean, we could put 201.4, but for a back of the napkin kind of calculation, I think that's only going to change this velocity by a tiny amount. They would tell you. Yeah, they would be very clear. And so if this was an AP question, what they would probably do is have him move to be a certain distance away from the center to make it very clear what you were supposed to do. But they're not going to have you try and decide whether you should fudge that number or not. That's not the way the exam's going to work. But for us, trying to do a little back of the napkin calculation, I think it's a little bit easier for us to do it that way. Is that okay? All right. No, you're fine. So calculating the kinetic energy, not a whole lot of work here, right? So I assume you all did 1/2 times 480 times 2 squared. Pretty straightforward, right? So that looks like 960 joules. Would you agree? Excellent. So over here, though, it's going to be 1/2 times 200 times 4.8 squared. Now here I'm at a loss. I mean, I don't know what 4.8 squared is. A little bit less than 25, but I don't know what it is. And then you have to multiply by 100, right? So what'd you guys get? A little louder? We didn't make a mistake. Where'd the energy come from? Now, this is an important question. It's something I need you guys to start grappling with. Momentum was conserved because there was no external torque on the system. I mean, we can talk about what happens as the guy walks to the center, but to cause a torque, there has to be a force that is applied at an angle to a torque arm. And in this case, he walks radially towards the center. And because of that, he never applies a torque to the merry-go-round. In any meaningful way, his motion, even though isn't truly a straight line because the platform is spinning, so he's kind of going in a spiral towards the center, he still doesn't apply an external torque. That's why the angular momentum before equals the angular momentum afterwards. But work had to be done because there's a change in kinetic energy. And if you've ever been on a merry-go-round, or you've ever been on like the teacup ride at Disney World, or if you've ever been on any spinning attraction where you're spinning or you're in control of how fast the ride spins, have you ever let your head fall back and regretted it? Like went to look up and then decided that was a bad idea? Have you ever noticed how hard it is to pick your head back up after you've done that? Now, this isn't accidental. Remember, there's still inertia working here, and we're spinning. So the guy, not the merry-go-round, but the guy has a velocity this way because it's spinning. And like anything else, he's traveling in a circular path, which means there has to be a force to deal with the centripetal acceleration required to go in the circle. Right? We don't forget that there's other physics properties at play here. This force probably is him holding on to the handrails and friction between his shoes and the ride. Now, if he wants to move towards the center, he has to push even harder than that to get towards the center. Right? He'll need to acquire more force because this force is just how much is required to stay in place. If he wants to start moving towards the center, he has to increase that to give himself some velocity. His motion towards the center does work on the device, increasing the energy of the device. And you guys probably know this. Near a merry-go-round, you would understand what it would take to get the merry-go-round to spin, right? You would just stand, say, here and give it a good push this way, and the merry-go-round would experience an external torque, and it would start to spin. Have you guys ever been on a merry-go-round before? Okay. Well, when I was a little kid, the way you did it was you ran towards the merry-go-round and jumped onto it. Does that sound like something that would work? Now, would it work if you ran toward the merry-go-round, say like that, and jumped onto it? Would it start to spin? No. If you wanted to spin, you could do it this way or you could do it that way. Those are your two choices, right? Depends on which direction you want it to get to spin. And maybe you and your other friends are going to all do it at the same time. The more of you jumping on at the same time, probably the faster it's going to go. All seems reasonable. Here's the question, and this part's the hard part. If angular momentum is conserved, the merry-go-round suddenly gains angular momentum. Did the kid have angular momentum before they jumped on the merry-go-round if they're just running in a straight line? And that just seems weird, but the answer is yes. The kid has angular momentum. We call this the angular momentum of a point mass. And it's kind of a weird idea. So let me at least write it out. Momentum of a linear point mass. Now, without the merry-go-round, so let me remove the merry-go-round, or try to. Stupid. Without the merry-go-round, the person running in a straight line wouldn't be said to have any angular momentum. They're just running in a straight line. They're not spinning about a pivot point. But when we bring the merry-go-round into our problem again, the problem is different because we know that the kid is going to interact with the merry-go-round. Because of that, from the reference point of the merry-go-round, the kid does have angular momentum. Now, this is a weird concept. It's not hard to calculate. It's not hard to use in practice, but it's a weird concept. And so it takes a little time to wrap your head around it. But this also will explain like why the angular momentum of a baseball bat can be translated into linear momentum of the baseball. It's the same process, or the angular momentum of a golf club being transformed into linear momentum of a golf ball. In all cases, we're talking about the transfer of momentum and energy, but you have to frame it correctly. And what that means is when we look at the kid as they run towards the merry-go-round, if you are the kid's friend and you're standing on the merry-go-round, then you can observe the kid as they run towards the merry-go-round. Does that make sense? Imagine the kid this time just runs past the merry-go-round. It doesn't jump on it. If you're the kid on the merry-go-round watching your friend, you'd have to swivel your head to watch them as they pass by. Does that make sense? So from the vantage point of the merry-go-round, the kid is traveling in a manner that makes you have to perceive a rotating reference frame to observe them, right? Because if you're watching them, if you're looking them in the eyes as they go by, you have to swivel to see them pass you. Does that make sense? So what we say is that the kid traveling in a straight line has angular momentum relative to the merry-go-round. Now, this only matters if the kid interacts with the merry-go-round. That's the only time it will matter. And we calculate this angular momentum, and you're going to love this. We use a lowercase script L for this version of angular momentum to help differentiate what we're calculating. And it's a vector quantity, just like regular angular momentum, because it has direction. But this part's the hard part, and I know it's going to be rough because it has a cross product in it. It is R cross P. Now, R represents the same thing we've kind of talked about. It's like a torque arm. It connects the point of rotation with the person who's running. So R in this case would be a line from the axis of rotation to where the kid is. That would be R. The kid's momentum is the same thing we would calculate for linear momentum. It's just mv. But R and V are vector quantities, so we have a cross product here in order to help us calculate what the actual angular momentum would be, and it involves this angle. So to calculate the angular momentum, it's R times P times the sine of the angle between those two. Now, I understand this part's a little weird, because if you're really paying attention, you realize that's going to be hard to calculate, because isn't R changing all the time? And isn't that angle changing all the time? Now, you would have to know where the kid starts to make this happen, to calculate this. But there is a shortcut. But in order to show you the shortcut, you're going to have to buy into a little geometry. So how confident are you that you can buy into a little bit of geometry? Okay, so what I want to do is, but to make it easier to watch, I'm going to say that this is the merry-go-round, and I'm going to draw a line that represents the path the kid would be going on until they make it to the merry-go-round. And I'm drawing it as close as I can to be a tangent. So the kid is running along this line, and let's consider, say, 4 places in the kid's path. Each one of them is going to have a different value for R and a different value for the angle. This last one is a kind of the point of closest approach, because it represents right when they're at the edge. So this is like they're right at the radius. Does that make sense? You good so far? Now, here's the thing. If we pick any one of the triangles that are here, and do you see that there's several triangles? Right, you see all of them? So let's look at the first one. Like this is R. Say R1, and this will be angle 1. And the kid's running with momentum P. So right now, the angular momentum when he's at position 1 is R1P sine phi 1. Okay so far? It's just how we calculate it. But let's advance to when they're at position 2. P doesn't change, but we now have R2, which is shorter, and phi 2, which is bigger. Good so far? Well, just working the math out, I would write this as R2P sine phi 2. I'm going to skip the third one because that's just repetitive, right? And I'm going to go all the way to the last one where this is just r, the radius of the merry-go-round. And this would be p, which still hasn't changed. This represents the instant they jump onto the merry-go-round. But that angle's got to be 90 degrees, right? So the last one, we'll say L4, is just the radius times p times the sine of 90 degrees. All okay? Everybody caught up to what I've written down and follow it okay? So consider this triangle for a minute. This is clearly a right triangle with the hypotenuse R1 and one of the sides R. You see that triangle okay? Is it clear to you that in that triangle, sine of phi is going to be R over R1? So isn't R going to be R1 sine phi 1? Do you guys see that okay? If I go to the next triangle, I'm now at phi 2, right? And R2, is it clear that sine phi 2 is going to be R over R2? Does that make sense so far? I'm just doing a little trig there. So wouldn't it be true that R2 sine phi 2 equals R? You may not be seeing what I'm doing, but in every one of these, R1 sine phi 1 and R2 sine phi 2 all equal the same value, just R, the point of closest approach, which is what I will call this. And what I'm intending to say is, although it looks like R and phi are changing all the time, the product of R and sine phi is the same value all the time. So as they're running, we don't need to know where they start. All we need to know is where they end up interacting with the merry-go-round. That's the only thing that matters. So although they may start way over here, we never need to know R1 in that angle. We just need to know how fast are they running and where do they land on the object. That's enough to know what their angular momentum is. So although technically this is how you calculate angular momentum, we in this class will almost always calculate angular momentum by looking at the point of closest approach. So we will write this as R perpendicular times P. Their point of closest approach is the point where R is perpendicular to their velocity. And that's usually when they jump on the object. This would also be what happens if it's a golf ball being hit by a golf club. The golf ball is going to leave at a right angle to the golf club. So thus the golf club's length is R, and the momentum of the golf ball is going to be the velocity here. So in all these cases, this is how we will calculate the angular momentum of a point mass, by just looking at the point of closest approach, the point where their velocity is perpendicular to their radius. Let's do an example so you can see how this works. Is that okay? So let's go back to our merry-go-round example, and let's have that 70-kilogram man run at the merry-go-round. So the merry-go-round has a moment of inertia of 200 kilogram meter squared, so it still has the same 2-meter radius. And imagine the guy running at it at a speed of, say, 3 meters per second, and they're still 70 kilograms. Want to know how fast will the merry-go-round be traveling when they run and jump onto the merry-go-round? So everybody understand the question? Well, understand it or not, we're not going to get to complete it. So we'll pick this right up on Monday.